Good afternoon, everyone. Sorry for the mistake. My name is Li Minqi from Peking University. Today, the topic of my presentation is hybrid Eulerian Lagrangian solver for high-speed reacting flows based on OpenFOAM validations. I will organize my presentation into the following 4 sections. First, I'll give you a brief introduction of my research background. OpenFOAM is an useful open source CFD platform. Rho central foam is originally density-based compressible solver inside it. It was usually used to simulate high-speed flows. Based on this specific solver, researchers further constructed Rho central RI foam, which added multi-species transport and chemical reactions. This solver is validated via simulations for one-dimensional and two-dimensional detonations. Furthermore, Zhang further constructed RY Rho central foam and further added a Eulerian Lagrangian solver. This solver is accurately validated through a series of benchmark cases, including inner shock tube case and the reactive shock tube case. Furthermore, this solver is applied to simulate multi-dimensional, multi-phase detonations. Then, based on the new version of OpenFOAM, Zhu added mixture average diffusion model, Eulerian Lagrangian solver, and AHI as chemistry solver. This solver is mainly validates the evolution of parameters for liquid phase and also tested the simulation of one-dimensional two-phase detonations. However, the platforms and codes I mentioned before are mostly in-house code, and it's hard for the other researchers to improve it and test it and apply it in their own simulations. As a result, we want to construct an open-source hybrid Eulerian Lagrangian solver DF high-speed foam to simulate high-speed reacting flows. Then I will briefly show you the structure of the high-speed foam. As for the solver for gas phase, the governing equations are listed here, and the marked source term mark the interaction between liquid phase and gas phase. Then the governing equations are solved mainly based on Rho central foam, and then we adapt the AMR, we adapt the Cantara to get the properties for transport and thermal, and get the source term for chemical reactions. After that, we further added the new time scheme called RK2SSP and RK3SSP. Also, based on the adaptive mesh refinement already constructed in OpenFOAM, we further added one-dimensional EMR to speed up the simulations for one-dimensional cases. Then, as for the liquid phase, there are the governing equations, and in the structure of OpenFOAM, it mainly contains 3 models. As for the first one, evaporation model, there are mainly there already have 2 sub-models to calculate the evaporation rate, which called liquid evaporation and liquid evaporation boil model. And then based on these 2 models, we did a little adjustment and constructed a new sub-model called liquid evaporation spotting. And then the second model is the droplet force model, and the last one is the heat transfer model. And then we adjust the update order of these 3 models and did a little adjustment to the calculation method of the droplet Reynolds number of these models and formed our own one. And therefore, when we get these properties, we can calculate the source term marked in the governing equations for the gas phase to simulate their interactions. Therefore, I will show you some validation cases and discussions based on it. The first one is the multi-component inner shock tube case, and the simulation setup is already listed here. And in this case, we turn off the chemical reactions, and we can get the result depicting the picture on the side of it. The present result we apply Eulerian time scheme, OLA time scheme, and RK2 SSP time scheme all show great consistency with the reference result. And this phenomenon would indicate that this solver have the ability to capture the flow discontinuity and capture the thermodynamics of multi-components. Also, since the result we get using RK2 SSP show great consistency with the result using Eulerian and the reference result, this could also validate our implement of this new time scheme. And then we further constructed reactive shock tube case. The initial condition of this case is marked on the side of it. And in this case, we turn on the chemical reactions, and we can get the process that the wave formed by the chemical reactions will chase up with a reflected shock wave. And then from the picture, from the result depicted in this picture, we can see that the present result we get using Eulerian time schemes are really close to the reference result. And this phenomenon could indicate that this solver has the ability to capture the interactions of convection and reactions. Furthermore, we further change the time scheme to RK2 SSP and RK3 SSP. And from this picture, we can see that all these lines are close to each other, and this result would validated our implement of this two-node time scheme and ensure the accuracy of them. Then we further tested one-dimensional detonation case. In this case, we get the detonation speed under a different equivalent ratio. And from this picture, we can see that the result we get using DFSP foam are show great consistency with the analytical result we calculated from SD top box. Also, in this case, we adapt AMR to speed up, and this picture shows the refined mesh using this approach. We can get that with AMR, the simulation can speed up by the factor of about 6.5, and further with the more implement of load balancing, the speed up factor would came to about 10. Furthermore, we test the two-dimensional detonation case. In this case, we apply a fine mesh, and from the picture of the instantaneous density field, we can see that the solver could capture the curved short front clearly. And from the picture of the history for maximum pressure, we can observe the regular circular structure clearly, and this could prove the ability of this solver to capture these specific structures. Furthermore, we do some validations for the liquid phase and discussions based on it. We first test the motion of single droplet in slow flow. The initial conditions for gas phase and liquid phase are listed here. In this case, we test the 3 different sizes of droplet. As they moved inside the tube, we could get its diameter and velocity at different locations. And this picture will show that the present simulation results are close to the reference result, and this would indicate that some models are accurate enough to capture the droplet parameters under slow flow conditions. Also, we noticed that we adapt 3 different evaporation models for these 3 different sizes of droplet. As for the droplets that have the maximum size, we apply the liquid evaporation model. And as for the liquid with medium size, we apply liquid evaporation boil model. And as for the droplet with the medium size, we apply the liquid evaporation spalling model. This phenomenon would indicate that maybe different evaporation models are suitable for different size of droplet, and this small conclusion may further instruct us in the following simulations. Furthermore, we test the coupling of droplets with shock waves. As the picture here, we could see the picture of the computational domain. In this case, a shock wave with Mach number of 1.25 would go through the droplet laden region, and the initial conditions for gas phase and liquid phase are listed here. In this case, we test the cloud of small particles with really small size and low mass loading. As the shock wave gets through this region, we could capture its movement, and as a result depicted here, the present simulation results show great consistency with the reference result and could clearly capture the discontinuity caused by the shock wave and capture the temperature drop behind the shock front because of the evaporation of the droplets. And this result would confirm the accuracy of this solver to capture the coupling process between droplets and shock waves. And then we have a task to simulate the two-phase pulsating detonations. In this case, we use the pre-shock tube to form a nearly stable detonation wave and let it into the droplet-laden region. The initial conditions for gas phase and liquid phase are listed here. And in this case, we test two different sizes of droplet and two different conditions for droplet equivalent ratio. As the simulation evolved, we could record the detonation speed at different times and record their evolution. From the picture here, we could see that with relatively large droplet equivalent ratio, we could observe low pulsating frequency. Also, since we tried different sizes of droplet, it would influence the number of particles inside one parcel. So this difference would bring the phase difference between red line and the blue line. Finally, I will give you a brief introduction of the validation process. As for DIF high-speed foam, the solver for gas phase would accurately capture the flow discontinuity, the thermodynamics of multi-components, and interactions of convection and reactions. Also, the implement of new time scheme RK2SSP and RK3SSP and one-dimensional EMR all works well in this solver. Also, as for the liquid phase, we validated the motion of single droplet in slow flow and test the coupling of droplets with shock wave. In the future plan, we will further complete the simulation for two-phase detonations and try another supersonic combustion cases to ensure the ability of this solver. That's all for my presentation. Thank you for listening.
Okay, thanks for Dr. Ling's presentation. Is there any questions?
I think this work is impressive because, in my opinion, most of Euler Lagrangian solver is for low speed or incomplete. So I have a question. Have you ever considered the discontinuity caused by material surface?
We have not considered it yet because our simulation is kind of for large size cases, and the more details about the surface of droplet or the physical phenomena inside it, we have not considered that yet.
Any other questions? Okay, I have several small questions. First of all, I want to say it's an interesting work, and I like it. First of all, I want to know that do you consider the viscosity in your server?
Yes, I consider that.
So, if you consider the viscosity, do you consider the turbulence?
Pardon?
Consider the turbulence.
Turbulence. We can say the in this case we only use laminar situation, and this solver could consider the turbulent conditions, but we have not tested it yet. But we will do it in the future.
In the simulation of the 2D, in the 2D simulation, because you have mentioned that you used the one-dimensional MR technology. I'm curious about if you do the 2D simulation, the MR technology is used the same or something different?
We used the 2D MR in our case, but maybe this approach we included reference to the other researchers, and we actually constructed our one-dimensional EMR based on it. So the EMR inside the deep flame could do both 3D, 2D, and 1D. Okay.
I'm curious about this server. Has this server been released with the latest deep flame?
Yeah, we will release it as soon as we can.
Okay, thank you.